For our third example, we're going to look at sine of x and see what else could happen with these intervals of convergence. Keep in mind the function for sine of x in sigma form was n from 0 to infinity, negative 1 to the n, all over 2n factorial, and then x to the 2n. Okay, so let's run our test. The first thing, again, we're going to do is we're going to use, in this time, the ratio test because of the factorials. So absolute value will ignore the negative 1. So it's just going to be x to the 2, parentheses n plus 1, all over 2, parentheses n plus 1, factorial, times the reciprocal of the original. And to force it to converge, we want this to be less than 1. Okay, so let's simplify a little bit. Limit as n approaches infinity, x to the 2n plus 2, all over 2n plus 2 factorial times 2n factorial over x to the 2n. Has to be less than 1. Okay, so let's rewrite. I'm going to rewrite the 2n plus 2 factorial and 2n plus 2, 2n plus 1, and then finally the 2n factorial. Okay, so things that'll cancel out. I'll cancel out the x to the 2n. That'll cancel the 2n. The 2n factorial will cancel out the 2n factorial. So all I should be left with is limit as n approaches infinity. And on top, I'm left with an x squared. And on the bottom, I'm left with a 2n plus 2 and a 2n plus 1. Okay, less than 1. Here's the deal, though. This is always going to be 0 because the bottom wins, goes to infinity. The x isn't affected by the limit. So that means this will always be less than 1. So what we'll say is this is always less than 1. Therefore, this is convergent everywhere, always convergent. Convergent everywhere. So our interval convergence would be all real numbers from negative infinity to infinity.